This lesson is part 2 on section 4.3 on empirical formulas. So, an empirical formula is the formula of a compound with the smallest whole number ratio of the elements. It might or might not be the actual formula, no matter what. Okay, it's just going to be the simplest ratio. Okay, an actual compound might be a multiple of the empirical formula. So we might solve for this and get, say, an empirical formula of HO, one hydrogen, one oxygen. That does not mean that that's the actual formula. That just means that that is the simplest ratio. Okay, this is called the empirical formula. All right, it would be like a 1-to-1 ratio here if you solved for that problem and you got HO. Though the actual formula might be H2O2, and that would be something called the molecular formula, which we will talk about actually in the next section. But today is about how to solve for empirical formulas, simply just given some basic information about a compound. So, the problem will say something like this. Determine the empirical formula of a compound that is 72.7% oxygen by mass and 27.3% carbon by mass. So there are a few steps to solve this. Step number 1, assume 100 grams of the compound exactly. Basically, if you do that, you can convert the percentages given to you in the problem into grams. So if we assume 100 grams of it, then that means 72.7 grams of the compound is oxygen and 27.3 grams of it is carbon. Well, and we've been spending time talking about how to convert from grams to moles in the last couple sections. So step 2, all right, this really isn't, step 1 really is just rewriting the percentages as grams. Step 2, convert each amount in grams to moles. Okay, so you're going to divide it by the molar mass of that particular element. So the 72.7 grams of oxygen divided by 16.00 grams per mole gives us 4.54 moles of oxygen. And then if we do that for carbon, 27.3 divided by 12.01 grams per mole, we get 2.27 moles of carbon. So first step, assume 100 grams. Second step, convert grams into moles by dividing by the molar mass of the elements involved. And we're then going to take those numbers and use them for step 3. Okay, so this is just repeating the problem up here. We're going to take those and look at them as a ratio, 4.54 to 2.27. Step 3 is to simplify by dividing each by the smallest number of moles present. Well, the smallest number of moles present in this example was 2.27. So we're going to take the 4.54 divided by 2.27. We're going to get 2, and 2.27 divided by 2.27 is 1. So we end up with a ratio of 2 oxygens for every 1 carbon. Right? So step 4, based on our information here, is to determine the formula. We have a 2-to-1 ratio of oxygen to carbon. Okay, that would be the percent by mass for something like carbon dioxide. Okay, simply just by looking at those percentages there. The really nice thing about these problems is that if you do them right, we should get very exact whole numbers. Now, every once in a while, you might end up with one, say, that is some sort of fraction, like 1.5, but we would know to then multiply it times 2 to get us to a whole number, and you'll see a few examples of those on the homework. So let's try this one together as an example. It says, determine the empirical formula of caffeine if it is 49.5% carbon, 5.2% hydrogen, and 28.8% nitrogen, and 16.5% oxygen by mass. So step 1 is to just assume that we have 100 grams of the compound and rewrite these as masses. Okay, 49.5 grams of carbon. Okay, we have 5.2 grams of hydrogen. We're going to divide by the molar masses here in a moment, so that's why I'm writing the line right now. 28.8 grams of nitrogen and 16.5 grams of oxygen. Okay. Step 2 is to turn them all into moles. So we just divide by the molar mass of that element. So the first one there, 49.5 grams of carbon, is going to be divided by the molar mass of carbon, which is 12.01. Okay, so let's see what that gets us. 49.5 divided by 12.01. That is 4.122 moles. I'm going to carry a couple extra significant figures just to make sure I get whole numbers at the end. 5.02 grams of hydrogen divided by hydrogen's molar mass. It's going to be pretty close to the same number, but not quite exactly the same. And we get 5.1485. Again, I'm carrying a few extra significant figures through the problem, okay, to help us out here towards the end. 28.8 grams of nitrogen divided by nitrogen's molar mass, 14.01 grams per mole. And that's going to give us 2.056 moles, and oxygen divided by 16.00 grams per mole is going to give us 1.031 moles of oxygen. I should include what element it is, okay, to make it a lot easier. Okay, so we got everything in moles. The next step, 3, was to divide by the smallest number of moles present. Well, the smallest number of moles present in this example is the amount of oxygen, 1.031. So we're going to divide each of them by that number and see what we come up with. So the first one, 4.122 divided by 1.031 is, we'll say, 3.998. So it looks pretty good, like that's going to be 4. Okay. The second one divided by 1.031. It's going to be pretty close to 5, 4.994. And 2.056 divided by 1.031 is 1.994. Okay, we'll say moles of carbon up there, moles of hydrogen here, moles of nitrogen there, and this one divided by the same number is just going to give us 1. So we get 1.031 moles, 1.000, right? They're all going to be the same thing. Moles of oxygen. And looks like I've got a pretty good set of whole numbers here. Looks like my formula is going to be C4H5N2O. And that's how you solve it. What can happen occasionally is we get a situation where our numbers don't work out perfectly as whole numbers. They end up as some kind of fraction that we then later have to multiply into a whole number. It's not really too hard, just one extra step you have to do towards the end. So we're going to do this one exactly in the same way. 40.68 grams of carbon, say divided by 12.01 grams per mole, okay, for the carbon. And that's going to give us, let's see here, 3.387 moles of C, 5.13 grams of hydrogen divided by 1.01 grams per mole, and that's going to give us, let's see here, 5.13 divided by 1.01, that is 5.079 moles of H, and 54.19 grams of oxygen divided by 16 grams per mole as its molar mass. That last one is 3.387 moles of oxygen. So dividing mole by the smallest one, well, 2 of them are the same number, which is kind of convenient. So we know what we're going to get with those. We know we're going to get 1 mole of carbon. We know we're going to get 1, I guess I'll put in the zeros, 1.00 moles of oxygen. The middle one, 5.079 divided by 3.387. This gives us 1.50 moles of H. Well, our formula cannot be CH1.50. Right? We can't have a fraction of a hydrogen atom. So what happens is, if we ever end up with some sort of a fraction here that's not a whole number, but could very easily be turned into a whole number, we end up multiplying the whole thing by an appropriate whole number. Since this is 1/2, right, 3 halves is a fraction, we can take and multiply this whole thing times 2. And we end up with the simplest whole number ratio. So instead of this CH1.50, we multiply everything times 2. This thing's empirical formula would be C2H3O2. And that would be the correct answer here. Even though as you're doing the problem, you might wind up with this in a weird 1 to 1.5 to 1 ratio, we know that if we multiply this number times 2, we get a whole number, so we just multiply everything times 2, and that would be my simplest whole number ratio. This would be the empirical formula and the correct answer. So just be aware that if that pops up, that's how you solve that issue.